8259 modes of operation is not covered. So that we'll try to see for first half an hour, and then next we'll try to see the 8257, the DMA controller, how it can be interfaced to 8086 so that you can do huge data transfer. Okay, so we will try to see that, and we will go ahead. Okay, so let us so this lecture of I'm trying to divide into two parts. The first half an hour I'll be giving you the details of the modes of operations of 8257 with an examples, and then the next we'll try to finish 8237, the DMA controller, and we finish by that. We'll finish the third chapter, then we'll move on to microcontroller from next class onwards. Okay, so now let us start with the content which we in the last class where we stopped our classes. So now let us try to see. In the last class we have tried to see in the 8259 with 8086. So how you are going to do that with 8086. So how many 8259s you can connect it to 8086. So in master and slave mode. So that's what we have seen. So with that, so then we started like what is interrupt, and how how you can interrupt the processor so that your task can be acknowledged or serviced by the microprocessor. And the next, if you have an 8259, so if you can do that hardware interrupting to 8086, we have only two pins, that is INTR and NMI. So to provide more number of interrupts so that more devices can be acknowledged, so then are serviced, then we can use 8259 in master and slave mode, so that around 64 devices you can interface to 8086 processor based systems, right? So that's so interfacing part is what we have seen in the last class, and then we'll try to see the modes of operations in this particular class with some examples. So coming to the operating modes, so the programmable interrupt controller can be operated in 6 modes. So one mode is fully nested mode. Next is special fully nested mode, automatic rotation mode, and specific rotating mode, and special marks mode, and pole mode. So there are the 6 modes the 8259 can work. So now I'll be dealing with 2 to 3, so that by this time we are running late. So what I'll try to do is I'll try to cover a few. So I'll try to cover what is fully nested mode, and then I'll try to cover automatic rotation mode. So the remaining mode you can go ahead on your own. So now let us see the modes of operation of 8259 is. So fully nested mode. So what is fully nested mode is, so in fully nested mode what we do is, so here you have your 8086, and here you have your 8259, and we have seen the interfacing between these two. So now 8259 has by using one single 8259 you can serve 7 devices. So 7 devices you can serve. So here you have IR0, here you have IR1, IR2. So interrupt request 0th device, first device, second device, so on up to 7th device. So in fully nested mode what we'll do is, in fully nested mode, IR0 has the highest priority, and next is IR1, next is IR2, so on up to IR7. So IR7 has the lowest priority, and IR0 has the highest priority in this fully nested mode is. So as you see this, 8259 has 3 resistors. One is interrupt. Uh, no, the resistors associated with 8259 already we have seen. Interrupt mask resistor, interrupt request resistor, and another one is interrupt service resistor. So interrupt service resistor. So the current interrupt which is serviced is stored by interrupt service resistor ISR. So you have 3 resistors. One is IR interrupt service resistor, interrupt mask resistor, and then priority resolver. You have priority resolver too. So in interrupt service resistor, this will be holding the resistors, containing the current interrupt which is being serviced. And then by using interrupt mask resistor, you can mask any one of the requests based on priority. So the priority resolver will select any one of the requests, okay, based on the priorities. And that depends upon the modes of the operation of 8259. So in fully nested mode, if 8259 is used in fully nested mode, then in fully nested mode, what we'll be doing is IR07 will be giving the highest priority by default, and IR1 is the next priority, and so on up to IR7 is the lowest priority is. So that is fully nested mode. So here what is the disadvantage of fully nested mode is, now let us take one device is getting serviced. Then here you have like now 7th device is serviced in the last. So in automatic rotation priority mode, what we do is, so here in some of the applications there are number of interrupting devices of equal priority. So then you may have the devices of equal priority. So in this mode, a device after being serviced receives the lowest priority, and so the device requesting an interrupt will have to wait. So in the worst case, until each of 7 other devices are serviced at most once, right? So then what we do here is, now let us try to take IR2 has the highest priority. Okay, IR2 has the highest priority in the beginning. So now let us try to take your device, 7 devices. You have IR0, IR1, IR2, so on up to IR7. So now if this is in the starting. So now IR2 is now just serviced. Okay, IR2 is now just service which has an highest priority. Now let us try to take. So then once that IR2 is serviced, then that will be given the least priority. That means this avoids, one device dominating the processor time. So that will be given the lowest priority, and the next device is given the highest and so forth. Right. So then if IR5 is, service that is having the next priority, so it will be on rotation mode. So automatic rotation priority mode. So here the device which is just service will be given the highest, means the least priority, so that all the other devices will be giving are being serviced. So the resistor associated with this automatic rotation priority is OCW2. Just remember. So in the last class we have seen there are 2 registers with there are initialization command words ICW and operational command word OCW. So these registers now need to be initialized so that you can use 8259 for any particular operations. Right? So there we'll try to see in detail what these bits are. So then this is specific, this is automatic rotation priority mode, and in specific rotation priority mode, what happens is the programmer can change priority by programming the bottom priority and thus fixing all other priorities. Here in specific rotation mode, what is this mode is, the programmer can change the priority by programming the bottom priority, and thus he will fix all other priorities. So now example, if you take IR2 is programmed as bottom priority. So IR2 is programmed as bottom priority. Then IR3 will have the highest one. So IR3 will have the highest one, then IR4, IR5, IR6, IR7, IR0, IR1, like that, IR2. Right, so the programmer has a choice of fixing of the bottom priority in specific rotation mode. So these are the three modes. Then other three modes you can go ahead. Now let us try to see few examples. And to set the priority command, right? So issued in OSW2. So OSW2 you have a bits called RL and SL. You have to make 1 and 1, and L0 to L2, the binary priority level code of the bottom priority device you can set. So OCW2 when we deal, then we will try to see this what exactly it is. So here you have at the end of the interrupts or interrupt subroutine that have non-specific EOI command and specific EOI command. Two commands will give. One is non-specific EOI command. So this command will reset the highest priority ISR bit. So this is because in nested mode it is the highest priority which will be in service. So there are, what we discussed here, now let us take, this is your 8086 processor, and then now let us take one, there is an interrupt. So then the processor, will stop the current executing program, and it stores that in stack, and then it goes to fetch the interrupt subroutine, address of interrupt subroutine from stack, and then it goes to that particular program, and then now it executes. So to return back to the main program at end of each interrupt subroutine, right, at the end of interrupts, then you have a non-specific EOI command and specific EOI command. That's what we are discussing here. So what do you mean by specific EOI command? So this command will reset the ISR bit which is specified as part of command. So 3-bit code L0 to L2 specifies which bit has to be reset in specific EOI command. And then you have automatic EOI. So that means in automatic EOI command need to not to be given. ISR reset by last INTA pulse. Okay, this particular automatic EOI is. Example if you try to take. Now let us try to see. This is there in Offenbach. Right. So now if you have the interrupt request registered, the priorities are like this. 0, 1, 2, 3, 4, 5, 6, 7. So now IR4, now let us take IR4 is in progress. Right, if it is in progress, then the priority of highest, right, so this is, at 6, and then next 7, then 0, and then 1, 2, 3, 4, and then 11. So IR6 service routine executes, and in the end, this interrupt, this bit is made 1. Right, so this is, this is service routine, when service routine resumes. So this is on rotate on non-specific EOI command, and if it is rotate on specific EOI command, then the execution will be like this. Right? So that is what. Now let us now try to see the initialization words and command words of 8259. So now coming to the initialization of 8259. So this is the flowchart you need to follow. Now there are now we will try to see only initialization command words. Only initialization command words we will try to see. So ICW1. So first to access now to use 8259 to serve all the interrupts. ICW1 and ICW2. These two initialization command words are first need to be initialized. Then 8259 it is you worked in or it is used in a master mode, or it is used in master mode, or it is used in slave mode. If it is in cascaded mode means what? One is it is in master's mode. So if it is using in master's mode, then there is a need of ICW4. Right, it is needed ICW4, right, and then if it is not in cascaded mode, So then it will check ICW4 is needed or not. There is no little thing. So ICW4 is needed or not. Just a second. Now. So here, so if it is in cascading mode, then only you need ICW4. So if ICW4 again, you know, you will, it is needed or not. If it is not needed, if it is needed, then you have to initialize. Then otherwise you have to accept the interrupt. That means if it is in masters mode, only ICW1 and ICW2, it is in standalone mode. Standalone mode means what? If 8259 is alone used, that means if you have a system which has only 7 devices need to be serviced, okay, getting, you know, interrupt from 7 devices only, then only initialization of ICW1 and ICW2 both are enough. If you are using, you know, 64 devices to the system which you are going ahead, so then I'm sorry, here, you know, just try to make a correction. That's what I'm just dealing with. So now this is what ICW3. This is what ICW3. So if the processor is accommodating 64 devices, then you are using 8259 in cascaded mode. So if it is in cascaded mode, ICW3 definitely need to be initialized. This is what the standard. Then only 7 devices if they are there, then these 2 registers you initialize. If at all, if you need ICW4, then you initialize. If you are not needing ICW4, then straight away you accept the request. So this is what the flow chart you need to follow. So I'll just summarize. If 8259 is servicing only 7 interrupts, it is working in standalone mode, then only 2 control votes, ICW1 and ICW2, you need to initialize. So then at that time, you just check whether ICW4 is needed or not. If it is needed, you initialize, otherwise you just accept the interrupts. If 8259 is worked as, is used in masters mode, by which it is accommodating 64 other devices, then ICW3 need to be initialized. Then you just check ICW4 is needed or not. If it is needed, then you accept the interrupts, right? So initialization command words, so there are 4 command words. And as we said, 8259 is given 2 IO port addresses. So then ICW1 is written using port 0 address of 8259, and ICW2 is written using port 1 address of 8259. So 8259 as a whole, you can give 2 IO ports addresses. So 2 IO port addresses, right? Okay. Then now let us try to see in detail about, that initialization of command words. Now let us go ahead. What exactly it is? Okay, and let us see few examples so that you can be thorough with the 8259. So now in initialization command word, we have seen already. This A0 should be 0, so A0 should be 0, right? And now this single SINGL, this bit, if this bit is 1, then 8259 is alone, it is used. If it is 0, means this is in cascaded, this D1. If IC4 is needed or not, if it is not needed, then 0. Then if it is needed, then make 1. We'll try to see what is IC4, whether ICW4, initialization command word, whether you need it or not. Then next one is ADI bit. So if it is 1, then the interval of 4, The call address interval. The call address interval, if it is 0, then the interval of 8. So this is AGI. Then LTIM bit. So that means, in interrupt, we have seen in the logics, there are, level trigger and then edge trigger. So where you have to accept, this is what your edge trigger. So during the edge transition, right, then you can take it as an interrupt. Level triggered means during this clock period, you can accept the interrupt. So based on the events are going to be serviced, whether that is 1 means level triggered and then 0 means edge triggered. This LTIM. D4 is 1 and then A6, A5 and A7. So they are the interrupt vector addresses. This is what you used for 8085 only. So you can put don't get condition here in the case of 8086. So now let us try to take an example based on the discussion what we have seen now. This is what your initialization command word to review back. So now let us try to see what value should be written into ICW1 in order to configure 8259 so that the ICW4 is needed in the initialization sequence. The system is going to use multiple 8259s and inputs are to be level sensitive. So it is a level triggered one. Assume that all unused bits are to be logic 0. So this is what some examples. So now here what he is saying, ICW4 is needed. So when ICW4 is needed, then here you write 1. So D0 you will write 1. And more number of 8259s are going to be used. So it is in cascaded mode. So D1 should be 0. Then and then level triggered or edge triggered. So then he mentioned the events now need to be serviced or level triggered. So when they are level triggered, this is 1. And the bits which are not used can be assumed to be unused bits are to be 0. So here now this is what we are discussing. So D0 is 1 and then cascaded mode D1 is 0. And at level sensitive inputs, then it should be 1 and then all other bits are 0 and D4 must be fixed to 1 to the logic level. So this D4 here is what, here D4 is 1, so it is by default 1. So now if you write these words, so then the initialization word now need to be written for this kind of example could be 19. So 19 hexadecimal is what now need to be written into the initialization command word for this kind of application. So now let us, this is what the first initialization command word we have seen. So now let us try to see the initialization command word 2. So the initialization command word has 8 bits. Now let us try to see what these bits are in detail. So this ICW2 selects the vector number used with interrupt request inputs. The vector number, so as we said, there are 256 software interrupts you can acknowledge. So each interrupt subroutine is stored in 4 bytes. One ISR is stored in 4 bytes. That's what we have seen, right? So this ICW2 selects the vector number used with interrupt request inputs. So if you're programming 8259, so it functions at vector location 080FH, place, right, then place 08H into this command word. If programming for vector 7 to 7H, then place 70 in ICW. So now let us try to take an example. So the bits are D0, D1, D2, D3, D0, D7 if you try to take. A8, A9, A10. Then you have T3, T4, T5, T6 and T7. And similarly that can be T3 or A11. So this D0 to D7 are labeled as D0 to D7 can be labeled as A8 to A15 of interrupt vector addresses. Interrupt vector addresses. So each vector, each interrupt vector table, interrupt subroutine is having 4 addresses, right? So this is used, by 8085. So we are not dealing 8085 now, 8086 only. So now we'll now D3 to D7 are labeled as T32 to 7 of interrupt vector type. Which type of interrupt we are using? So used by 8086. So now just focus on these 2 bits only, T3, T6, T5, T4 and T3. Then remaining you don't care about it. Right. So now let us try to take an example. So here this T3, and that means interrupt vector type. Interrupt vector type can be specified by using these bits in ICW2. So now let us try to take an example. So what should be programmed into register ICW2 if the type numbers output on the bus by the device are to be ranged from F0 to F7? Try to take this example. What should be programmed onto ICW2 initialization command mode if the type numbers of the output on the bus by the device are to be ranged from F0 to F7? So that means the total 256 types of interrupts. So type 0, as we said, type 0 is divided by 0. So type 0 is divided by 0. So this is type 0 interrupt. Like that you have 256 types of interrupts are there. So the type numbers output on the bus by the device are to be ranged from F0 to F7. So now let us take 7 types they are, the interrupts. Then the type of the interrupt can be initialized on this ICW2. So F0 now if you try to take this 1 1 1 1, then 0, the rest that you can take it as 0. So then this is F0 means D7 D6 D5 D4 R111, right, 111, and the lower 3 bits are don't care, right, that is not used, that is used by 8085, so don't worry about it. So then that initialization command word 2 now is loaded with F0. So this means the type of interrupt which occurs is loaded in initialization command word 2. Is it all right? So now let us take this example. Write the initialization instruction for 8259 interrupt controller to meet the following specifications. So interrupt type is 32, edge triggered, single and ICW4 needed. Mask interrupts IR1 and IR3. So now this is what one example. A good example you can consider. So now I think whether it is visible or not, I'm not sure. So what you can do is, so write an initialization. So now this is what the application is. Write an initialization instruction for 8259 interrupt controller to meet the following specifications. The interrupt type is 32. That means which initialization command word 2 now need to be loaded with this. Then there is edge trigger. Then ICW1 corresponding bits need to be initialized. Single only 8259 is used and ICW4 is needed. Okay. Then mask interrupts IR1 and IR3. Okay. That means specific auto rotation mode you can mask the interrupts IR1 and IR3. So then what need to be written? So now if you try to take these bits, right, so ICW4 is needed and it is single, right, so then edge triggered, and now all these things if you consider, you have to write 13H in ICW1. Then ICW2 interrupt 32. So interrupt 32 here now if you try to see, this interrupt 32 is in decimal. So decimal, which is 32, hexadecimal it is in 20. So hexadecimal it is 20 means these bits if you try to see T7 to these bits if you try to see D7 to these bits 2, 0, 0, 1, 0, then rest are don't care. Right, so this bit, anyhow this is 0. So 32 interrupt until unless it is mentioned. So this is in decimal, so in hexadecimal. So this is 0, 0, 1, 0 and 0, 0, 0, 0. So then this is what the initialization command word you want to, and you can write into ICW3. So we are not using a slave, so then ICW3 is not needed. So and ICW4 exam, the only reason we need to send an ICW4 to let the 8259 know that it is operating in 8086 system. Okay, so ICW4 is needed in 8086 system. So the significance of ICW4 it is given here. So the only reason we need to send ICW4 is to let 829, that means 8259 can be used with 8086 microprocessor. It can be used with 8085 microprocessor. So if it is used with 8085, so in the beginning it is designed like that by Intel. So 8086 environment it is to indicate that ICW4 is needed, right? So that is what. Now let us see the program now for this kind of application, right? So for masking anyhow we need OCW1. So we will try to see what is that OCW1. But now if you try to see this program, move AL comma 13, then out AL comma 40, right? And then move AL comma 20. So the type of interrupt, and then that you are writing at 41. So ICW1, that means 40 and 41 are the port addresses of this initialization command word and initialization command word 2. So then move AL comma 01, 8086 mode, so that you are writing at 41. Right, so this is a small piece of code you can write. Now one more example if you try to consider. Write an initialization routine to program 8259 in the following thing. So jump table on vector address 80 and rising edge trigger, rising edge trigger, and rising edge trigger, IR0 and IR1 should be masked and rotating equal priority. So for that, ICW2 is 80H. So the 80H address is, you can consider this 1 and 000, and then this is 0. So 80H, this is ICW2, and ICW1. Then you can see rising edge. So it means edge triggered, and ICW4 is needed 8086. So then it is. No, single you are using or cascading you are using. Now this is 1 by default. So 13H what you can try to write. And ICW4, and now we'll try to see ICW4. This ICW4 is need to transfer the microprocessor in 8086. So buffered or non-buffered is not given, always assume buffered system. So what is that? Now we'll try to see this ICW4 is, and this is what the command word, which is OCW1. For this kind of application, IR0 and IR1 should be masked, right? Then OCW2, these two registers we will try to see now, and a small piece of code you can write for initialization of this. So now in ICW3 description, if you try to see, ICW3 is used only when ICW1 indicates the system is operated in cascaded mode, and in cascaded mode the bits of ICW3, right? So now in cascading mode you can go ahead, and then ICW4 is programmed for use with 8086 to Pentium 4 processors when you are designing your computers or something based on this. And the rightmost bit must be logic 1 to select operation with them. In ICW4, the last bit should be 1, indicating that it is working with 8086 to Pentium. 70M. And remaining bits are programmed as follows. SFNM, it selects the special fully nested mode of operating if logic 1 is placed in this bit. So special fully nested mode, and buffer and MS, buffer and master slave are used together to select the buffered operation or non-buffered operation of 82599 as a master or slave. That is ICW4. So few examples also we have seen. And now the next thing is we have to deal with operational command words. OCW1, OCW2, OCW3. So there are 3 operational command words. So like 8259 can work with 6 modes, right? The fully nested mode, rotation mode, automatic rotation mode, specific rotation mode, and all we have seen. So it has to be work in that means. Now you have to configure your 8259 here like this. Now if you try to see, this command word is used to mask out unwanted interrupt request. So when 7 devices, when they are connected, so some devices, if they are not needed for one particular application, then you can mask them. So now what you can do, so port 1 means this A0 is 1 is what you can consider, this operational command word, right? Port 1 is what you can use. And now M is 1 indicates the interrupt request. So M is 1 indicates the interrupt request input is masked or disabled. It has to be, so you have 7, right? So IR0 to IR7, you have 7 interrupt requests. So if you want to disable them, then you make that 1. And if you want to enable that, then you make it 1. So then now you can use this. So IR0 and IR1 is what you can indicate here. Then if you want to mask, if you want to disable, then write 1 and then remaining are 0. This is operational command word. So now, for example, if you try to take, what should be the operational command word code if the interrupt input IR0 through IR3 are to be masked and IR4 through IR7 to be unmasked. So now if you try to see, so for masking you are writing 1 and then you are writing 0 at D4 to D7. So then 0F is the command word which you need to write into operational command word. So now this example, if you now consider IR0 and IR1 should be masked. So then there you write 1, then that is what it is there here. There you write 1, then all are 0. So 03 is the operational command word. So this is what the initialization is. Right. And then operational command word 2. So now here you have L0 to L2. Right. So the level. So the level you can 7 level 000, 001, 010, 011, 1004, 1015, 1106, 1117. So that levels, the IR levels to be acted upon can be mentioned here, but with its equivalent binary thing. So then these bits R, SL and EOI. So this R, SL and EOI is non-specific EOI command and specific EOI command. So you have to write these things like non-specific EOI or specific EOI at the end of your interrupt subroutine. Now based on that you can enter here in this operational command word. So now here, now if you try to take, so now if you try to take here, so these are the things you have to enter here, quotes, right? So example, if you try to take the last example, what operational command word 2 must be issued to 8259 if the priority scheme rotate on non-specific EOI command is to be selected. So non-specific, so if the priority scheme is rotated on non-specific EOI command to be selected. So non-specific command means, now you try to see, so this non-specific EOI is 20. So then 20, right? So at that particular bit and the level you have to mention, that is a 000 and then these bits, this is what the command word you need to write into this thing. So these are the operational command words. You can go ahead and now you can take a number of examples. Write an operational control word for a fully nested priority structure masking IR1, IR3 and IR5 and enabling ISR for read operation. What code should be used and at the end of each interrupt service routine. So now you can take that and then now you try to see ICW1 port address interrupt marks word is this, right? So for this kind of applications you can go ahead. So now coming to the application, this is so I'll just discuss only one application and then I'll close this 8259. Right. So now let us try to see. An 8259 is interfaced to an 8086 processor like this. So analyze the circuit shown in figure and write an appropriate main program and service routine that counts as a decimal number the positive edges of the clock signal applied to IR0 input of 8259. So there is a clock input, right? Clock input to IR0. Now what you need to do, at the positive edges of the clock, you have to count it, and the decimal number equivalent 1 is what now needs to be stored. So you have to write a main program whenever there is a clock, then you just go there and count and come back. So you have a main program, and from main program, whenever there is a clock, you go there and then count it and then come back. So write a program, a main program and a service routine. So a main program and service routine that counts as a decimal number the positive edges of the clock. So now this we are doing from long back. So now you can decode what is the logic, this one. So this is what your AND gate, this is what your NAND gate, then this is your NOR gate. So equivalent decoding logic port addresses you can go ahead. So now we will try to see the flow chart. So now first you define your different segments in main program. Where is your data segment? Where is your stack segment? Okay, and then stack pointer pointing out to that particular memory location as. So this is what your main program starts with somewhere in the code segment, right? So when there is an interrupt, when there is a clock, so then what you do? So then which kind of interrupt vector that is, based on that you initialize 8259 and enable interrupts, right? And then from that you just go to the interrupt subroutine. So the interrupt subroutine is this. Save the processor status now, increment the count, okay, increment the count and restore the processor status now. So the count you increment whenever there is a clock. You don't know when exactly the clock, there is a positive edge, right? Positive edge. When the clock you are getting, you don't know. So then what you do? So you just increment the counter and then now you just restore back the processor and then return. And then processor will do it. It is as usual task. Whenever there is an interrupt, then it initialize, anyhow you initialize this kind of interrupt it is, right? Then it counts that and then it comes back. It counts that and it comes back. So this you can write a simple program based on this. One more example of 8259. Generate a real-time clock by generating periodic interrupt request signal on NMI input of 8086. Generate a real-time clock by generating a periodic interrupt request signal on NMI input of 8086. So this 4060 is a CMOS IC which is 14-stage ripple carry binary counter. And it is a counter or divider and oscillator. So now this one, it is what it is giving. It is generating a real-time clock by a periodic. That means whenever there is a clock, then that particular periodic interrupt you will give it to on NMI of your 8086. Then the program is this, right? So the main program is this. So your initialization of the command words, you can do it, and whenever there is, then you can write a simple subroutine, and then you can go ahead. So like this, in PCXT, in personal computer, in extended technology, in the first personal computer when it is proposed, PCXT, then the address for this 8259 is given like this. So ICWRs and OCWRs, the addresses are given 20, 21, ICW1, ICW2, ICW3 and ICW4 21, and OCW2 20 and OCW1 is 21. These are the port addresses given in personal computer XT, okay, in our personal computer in the beginning. And IBM PC, okay, the request levels are like this. No, PC80, advanced technology in personal computer, the advanced technology, serial ports, no, the devices addresses are given like this. This is interrupt controller 1 and interrupt controller 2. Two interrupt controllers are used in PC80, 90, 86 and 90. So, right. So, to examine the type and quantity of hardware interrupts received by Linux system, use the cat command to view the interrupt. So now if your operating system is like this, if you want to see your 8259 where it is in your computer, then you can give these commands. Okay. So this is what 8259, right? 8259. So here mainly you have to focus so that it will generate two addresses 8000, 8002, two addresses for initialization command words and operational command words. So two IP addresses, and then you can interface to your 8086, and for a number of devices have to be connected. Based on that, you can initialization command word and operational command word, both you can initialize, and then you can start writing code. And in the last, I have shown you how this 8259 is used in PC80 and PCXT computers in olden days, right? So with that, we'll finish 8259, the programmable interrupt controller, which is very important application is. Right? The same thing I try to show you in 8051 and Atmel microcontroller. If these concepts they are clear, then the same thing we can extend it to microcontroller. You know, like you may not be needing all the facilities which computer needs in microcontroller, but interrupt, if a controller has to service in the different devices, then you may be needing these fundamentals by where you can apply. So I'm spending here a little bit time so that whenever we go to microcontroller, simply we can because these concepts we have, like what is interrupt, when interrupt occurs what happens, then what is nested ISR, and then so all these things we have seen, right? So now let us go ahead with the next topic, that is 8237. So now let us try to see the next topic, that is micro direct memory access. One more interfacing chip we need, and very important in memory transfers too, right? So now let us go ahead with the next topic, that is DMA controller. So 8257 is an IC. Sir, we are discussing all these things, but where they are, you may have a question. So in computer, if all the devices, in your motherboard, other devices like, CD drive, pen drive, okay, printer, everything you are getting serviced by your processor, right? And which could be done nowadays i3, i7. So we are discussing, 8086 interface. In olden days, these interfacing chips, they are available on the motherboard in North Bridge and South Bridge. Okay, and now they are available on chip of the microprocessor. Don't think like we are studying some ICs which are not used or which are not there. No, these i3 and i7, they are 80x86 processors. Once you have the processor concept, then understanding computer architecture is very simple. So this IC 8257 is a special IC. It is proposed by Intel, right? It is manufactured by Intel for direct memory accessing this. So now we'll try to see what exactly this direct memory access is. So direct memory access is a process in which an external device takes over the control of system bus from the CPU. Right. So now this, let me um, let me give you this with the help of this thing. So now let me take a slide. Now it's very simple. 82, the need for 8257 is what we'll try to see in this particular half an hour session. This is what your 8086 microprocessor based system or CPU even call. This is what your CPU. So here you have a memory. Here you have a memory. Now in the CPU you are putting a pen drive. Okay, so pen drive. Now the data now from pen drive to memory of the computer you can send, or from memory to pen drive you can copy some data. Take this kind of example. So any task it is done in computer based systems where microprocessor is your CPU, then with the acknowledgement of CPU only the data has to be getting transferred. So this process, if you involve the microprocessor, then this device will request the processor like you want to send the data. Then the processor it transfers the data into the memory. So it needs 2 clock cycles, which is very, very slow. So I want direct memory access. Means what? I can transfer directly from memory to peripherals, IO peripherals, or IO peripherals to memory. This is called direct memory access, DMA. Right, now we'll try to see what exactly this is. So now, if you try to take one example, what is this DMA? And now let me give in figures why DMA it's important. Here you have 8237 and 57. 8257 is advanced version, right? So now there is an example. Let me give you. One example. I want to give you one example. Why processor is not involved in data transfer? Right, within nanoseconds you have to send some. That means if you take any hard disk, the hard disk can send in nanoseconds some, let us take 100 bytes. That much fast it has to do data transfer, but involve microprocessor in it, then it will become a little slow. So this data transfer you can do it, in this example, what you can do here what you can do is, You write a program in the memory so that it transfers the data from memory to peripheral, which is very slow, is what we are now claiming. So now for that, if you write a program, then how the program takes. Now let us try to write, I am writing a software program which will transfer the data. Now let us try to see. So now how many bytes you want, that those many number of bytes you try to give it in the counter. And move dx comma the port address where you want to move the data. Move al comma contents of si. So that means this is what your memory in which you have, let us take 100 bytes of data. Right, 100 bytes of data, 10000 to 100 bytes you can consider. 100 equivalent is 10064H. So 100 bytes of data is here. So now this data now need to be transferred to a pen drive. 100 bytes of data. So you can write a program in your code segment like this. Move al comma contents of si. So this right. From outside to memory you are this program is from outside, because dx means from outside, pen drive address can be loaded into dx. Move al comma contents of si, right, then out al comma dx, then you increment dx, increment si, then come back, move that into memory. So move that byte into memory, and then that you move it, you just out that, okay, out that into a particular memory location. Right. So now this is a simple example. In memory, 100 bytes now need to be stored. Right, 100 bytes are stored, and now these 100 bytes now need to be sent to a pen drive. Right. So the pen drive address is somewhere around 8000. This address you are writing here, move dx comma port address. So now you are indicating this with an SI, and you are copying the content into AL, and that into your. So every time when the processor is doing, the processor is held up here. It will not do any other task. So then what you can do is, in these kind of applications, so in this kind of applications, what you can do, you can use a DMA controller. So this is what your microprocessor, this is what your memory. Any device that is hard disk or pen drive or CD drive or any IO device, the DMA will take care of the control of the buses, and then it will keep on transferring data from memory to the IO, so that the speed is very fast. Okay, the speed of the data transfer is very fast, right? So this is what the DMA controller does, direct memory access. Means without the microprocessor, the DMA controller will transfer memory to IO or IO to memory directly. That is DMA. So then the processor has to do, it has to send the beginning address in the memory, and then block length and port ID, and then that is it has to be done. So now let us try to explain this with the help of this diagram. The DMA and DMA thing is. So now let us try to understand the sequence of this. So 8086's microprocessor is your master, which does every task. But here we do with the inclusion of microprocessor, the task is becoming slow. So then what the DMA controller does is, if a peripheral device is ready to transfer the data, then it gives a signal like device request. It indicates that yes, data is with me, I want to transfer it to the memory. from pen drive to memory is what you can try to take. So then if it is a valid request, then the DMA controller, what it does is it has a pin called hold request, and this hold request is connected to hold pin of 8086. So it makes this high. So when there is high on this hold pin, the microprocessor, if it is a valid request, then microprocessor gives the permission of using its address bus, data bus, control bus by the DMA controller. So it gives a hold acknowledge saying that yes, now you can use the buses. So this when hold acknowledge, when it gets, then the device, then the controller will use the device acknowledge, yes, you can transfer data now through the buses available. Right. So the DMA controller transfers the bytes into the memory. This is what your DMA controller in microprocessor systems. Right. So now coming to the data transfer, the mode of data transfer, there are three modes of data transfer. One is single byte transfer is what we can call, and another one is cycle stealing. Single byte transfer or cycle stealing DMA. So this is the first mode of operation. When my DMA controller is transferring data, it transfers the data in three ways. One way is single byte transfer or cycle stealing DMA. In cycle stealing DMA, what it does is, if you have a machine cycle, so the total, the number of clocks in which, in the first machine cycle, if the processor, if it is doing its task, some other task, then DMA steals a cycle. That means, in between, the DMA clinches the control of the address and data bus so that the DMA will perform next cycle. Then the next one is processor will perform. The next one is DMA will steal the control of the address and data buses. So on it goes on. This is called cycle stealing mode. That means, the processor and DMA both they share the bus. Right. So this is called cycle stealing mode. So the steps involved in cycle stealing mode are start, initialize DMA controller. So you need to do DMA controller initialization. Enable DMA channel through which you want to transfer your data. Send hold signal to the microprocessor. If the processor is giving hold acknowledge, yes means you go, otherwise you wait until the processor gives the acknowledgement. Yes, if it is given hold acknowledge, let us say it is received, so then you transfer a byte from memory to IO or vice versa, IO to memory, right? Then disable hold signal, okay, disable hold signal and enter into slave mode. Right, and then increment the address register, increment the address register. If the count is becoming 0, then the DMA operation ends. Otherwise, again it sends the hold signal the next clock cycle. Right, so like it steals the cycles and then it will go ahead. So the same thing it is written like single byte transfer. And now the same thing it is written in the form of the number of steps. You can use it as a notes. The IO device asserts DRQ line when it is ready to transfer data. The DMA asserts hold acknowledge line to the request to use the buses from the microprocessor. The microprocessor asserts hold acknowledge granting the control of the buses. DMA asserts device acknowledge to the requesting IO device and executes DMA bus cycle, resulting in the data transfer. Then IO devices deserts the DRQ after data transfer of 1 byte of word. Then DMA, it disables the dark line so that microprocessor again retains the control of the address buses. So this is one way of data transfer, cycle stealing DMA, which is we call cycle stealing DMA. And coming to the burst or block transfer DMA. So in block transfer DMA, what it does is the processor, now let us take, in one cycle it is doing one particular operation. Then the DMA will take, longer cycles to transfer the memory so that the other task will be getting slower in this block transfer. When the entire data transfer, when it is done, then only the processor gains the control of the address buses. So this is block transfer, burst method or block transfer DMA. A block transfer DMA. So then coming to this here, this is written in the form of flow chart. So now you initialize DMA controller, enable DMA channel, send hold acknowledge to the microprocessor. If hold acknowledge is received, if it is received, transfer a byte from memory to IO or IO to memory, right? So you decrement the address register and increment the control register. So you increment the control register up to the control done to transfer the address bytes. And if it is done, then DMA was suspend operation and hold signal will become 0. Then processor regains the address. This is the burst mode. Block transfer mode or burst mode. Same thing. If the device is ready to transfer data, then DMA acquires the control of the buses processor. So transfers 1 byte. Is the terminal count exhaust? Terminal count, if it is not exhaust, then device is, if it is ready to transfer data, yes, then go ahead. Right. Then if no, then you wait until it's ready. So then the processor need to wait here in this particular thing. So this is block transfer. So this is written in the form of steps. So what we have seen, in flow chart, right? The one after another is block transfer or burst transfer, right? Then next one is the demand transfer. So in demand transfer in DMA, what it does is, if the IO device is ready for data transfer, yes, then the DMA acquires the control of the bus from the processor, transfers 1 byte. Is the terminal count exhausted? Yes. Then stop. No. If the device is ready for data transfer? Yes. Then it will go ahead. This is what your demand transfer, which is similar to this. So what we have discussed up to now, to increase the speed of data transfer between IO devices and memory, Intel designed an IC called 8257. The features of this IC are, it is 4-channel DMA. It has 4 IO devices can be interfaced to DMA, and it is designed by Intel. An enhanced channel has 16-bit address and 14-bit counter. It has 16-bit address and 14-bit counter. 14-bit counter, make it a mine. And it provides chip priority resolver that resolves priority of channels in fixed or rotating mode. So 4 devices can be transferred data here. So then the priority among the 4 devices can be provided. So there is a priority resolver, and it provides on-chip channel inbuilt logic. And it generates a terminal count signal to indicate the peripheral that the program number of data bytes have been transferred. Once the transfer is done, the 8257 generates a signal called TC, terminal on count. And it generates mark signal, is important. TC and mark both are important. This mark signal to indicate peripheral that 128 bytes have been transferred. Every 128 bytes when the DMA transfers, then it generates a signal mark. Terminal count means the number of data bytes have been transferred. Every time the terminal count, it indicates the number of terminal count. 128 bytes mark. It requires single phase clock. And the maximum frequency is 3 megahertz and minimum frequency is 250 megahertz. This is the difference between 8257 and 8237. 8257 can work with the frequency of 3 megahertz. 8237 frequency of 1 megahertz. And it executes 3 DMA cycles. The 3 DMA cycles are DMA read, DMA write and DMA verify. These are the 3. And now the pin diagram of DMA controller, if you try to see, this is 8257, 40 pin IC. It is a 40 pin IC. And now if you try to see the details of this, so this 40 pins, so it can accommodate 4 devices at a time. So it has 4 channels. Now if you try to, this is very simple, direct memory access, DMA. Direct memory access, DMA. It has 4 channels. Now you try to see. This is channel 0, channel 1, channel 2, channel 3. And here you have address and then counters. So counter is 14 counter, 14 bit counter, 14 bit counter, 14 bit counter. So 4 devices you can connect, 1, 2, 3 and 4. Each device, when it is ready to transfer data, it will give DRQ signal. So in this device DRQ signal, this device DRQ signal, this device DRQ signal. When there is a DRQ signal, then the 8257 has one signal, that is hold request signal, HRQ. This HRQ you will connect it to HOLD, hold signal of microprocessor. When it is a valid request, then it gives hold acknowledgement. When it is given hold acknowledgement, then the DMA will transfer the data from the device, from memory to the device. Okay, memory to the device or device to the memory. So here you have 4 channels, channel 0 and channel 1. And this is bidirectional data bus. From memory to the processor or processor to the memory. So this is internal data bus. Right, the data bus of 8257, it is D0 to D7, 8 bit at a time it can transfer. Right? Okay, and then TC, terminal count, just now we have seen, mark is one signal. Mark means what? 8257 generates one signal called mark after 128 byte transfer. So this is mark. TC means terminal count. Each byte data transfer is indicated by using a terminal count. Then you can read. Such few registers are associated with it. And there is a priority resolver. So this priority resolver will resolve the priority among these devices, or disk or pen drive or CD drive or floppy drive, which has to be given highest priority. Right. And then here you have control logic and mode set logic. Control logic and mode set logic. Right. This ADSTB is also an important signal. This A0 to A7, these are the few signals. Right now let us see that in detail. So the pins and signals of 8257. So DRQ0 to DY, this thing, DB0 to DB7, A0 to A7, and ADSTB AEN, ready, reset. Right. IOR, IOW, memory read, memory write. This is 8057. Now let us try to see each and pin description. D0 to D7, these are bidirectional tri-state buffers. Right, so this thing you can go easily. IOW, it is low tri-state buffer bidirectional control line. In the slave mode, it functions as input line. And so 8257, it can be worked in slave mode or in master's mode. Slave mode means, processor. When it is master, then 8257 is slave. When 827 is getting the control, then 8257 becomes master, and then you can interface to clock and reset A0. So these are the tri-state buffered bidirectional address lines. In slave mode, these lines are used to address input lines and internally decode access to internal registers. In master mode, these lines are used to address the output lines A0 to A3 bits of memory address on the lines. Chip select A4 to A7. So A4 to A7. So in slave mode, these lines are used as address output lines. Address output line means, in master mode, from where to where the data has to be transferred, indicated by this A4 to A7. You have ready signal, HRQ signal, hold acknowledge signal, memory read signal, memory write signal, right, address enable signal, right, and ADSB. So this ADSTB is split data and address line. It is used to split data and address line. It is working in master mode only. In slave mode, it is ignored. So this is terminal count. This is mark. So this is DVAR queue, and then this pins and all we know. So this is what you just keep in mind. So the addresses and IO functions of 8237. If you want to use 8237 or 8257, these many address lines. Now let us try to see A0, A1, A2, and A3. When they are 100, read bar is 0 and write bar is 1, read status register. There are two registers with 8257. One is status register, another one is command register. In command register, you can configure or initialize 8257 as in two modes, like you have priority also, priority setting and all. So that you can give it in command register. And when it is transferring the data, the status of the DMA, you can read it in status register. So this is write request register. So write single mask register bit. So these are the different commands. 100, 100, 100, 101. Then it is illegal and all. So this is what the block diagram. So it has containing 5 blocks. That's what we have already seen. So now let us try to take an example. So now you have two registers with 8257. One is mode set register, another one is status register. So what is this mode set register? So it is used to set the operating modes. These registers are programmed after initialization of DMA channels. So here you have D0 to D7 bits. So this D0 to D3 are for enabling 4 channels. Channel 0, channel 1, channel 2, channel 3. 4 channels are there. Enabling or disabling of those channels by using this. So now this is RP, EW, TCS and AL. When AL is 1, then it is in auto load mode. When AL is 0, then it is in rotating mode. So 2 modes, AL, rotating mode and auto loading mode. And when TCS is 1, then stop after terminal count, disable the channel, right, terminal count, and if it is 0, then start after terminal count, enable the channel. And extend write mode and normal mode. Rotating priority, fixed priority among the 4 channels. If it is 1, rotating priority, 0, fixed priority. EN3 bit, if it is 1, then enable DMA channel 3. If it is 0, then disable channel 3. So like that, 1 and then 0, 4 channels enable, disable. Now next is status register. So it tells the status of the DMA channels. So this TC status bits are set when TC signal is activated for that particular channel. So update flag is not affected during the read operation. So now if you try to see here, you have the status register D0, D1, D2, D3, D4. So then TC0 to TC3, then upgrade. So now update flag Right. If it is 1 means 8257 is executing update cycle, 0 means it is executing DMA cycle. And DC3 is 1 means it is activating channel 3 and 0 means activating channel. So channel first you need to activate. So channels like that you have 4 channels. So 4 channel bits. TC1, right. So then the address of the status register is this in this kind of thing. Right. So now let us take an example. So coming to the modes of operation of 8254, you have rotating priority mode and you have fixed priority rotating mode. So in rotating priority mode, the priority of the channels has a circular sequence in rotating priority mode. In fixed priority mode, this priority is fixed. TC stop mode, auto load mode and extended write mode. There are 3 modes again in fixed priority mode. So in fixed priority mode, fixed priority, highest channel 0 is given highest priority, channel 1 is given next priority, channel 3 is given the next priority. In rotating priority mode, this is in a circular sequence, channel 0, channel 1, channel 2, channel 3. So in rotating priority mode, now let us take the DMA is transferring data from the devices. Now let us take it is servicing device 1, right, one particular channel 1. So then in the next sequence the channel 1 will be given the highest priority, then next one will be given the lowest, next one will be lowest. So this is what the rotating priority is. These are the modes. So coming to the DMA cycles has 3. When DMA takes over the control of the bus, it performs 3 tasks. One is DMA read, another one is DMA write, another one is DMA verify. So in DMA read, in this cycle, the data is transferred from memory to I/O. In DMA write, the data transfer is from I/O device to memory. In DMA verifying, the data is not transferred between memory and I/O, but it is used by the peripheral device to verify the data has been recently transferred or not. So that is DMA verify. So to avoid the overwriting registers of channel 3, update flags in the start register so that it is monitored by the CPU. So 3 tasks the DMA cycle. In DMA cycle 3 tasks are done. DMA read, DMA write and DMA verify. So these are the addresses given for DMA. These are the addresses are given. Channel 0 DMA address, channel 0 terminal count 80s and 81. Channel 1 DMA address, channel 0 terminal count. So these many addresses you need if you have DMA controller in your system, computer. Mode set register is 88, status register is 8B. So this is what interfacing of 8085, but you can go ahead with 8086 also. Plus 138, and then now you can try to see this A4. Now you see this is OR gate equivalent, so then this is 1 0 0 0 80, and then next thing are decoded by using this, right, 74 LS 138 and can be connected to 8237. So 4 devices, 1 2 3 4 devices are connected to 4 channels of your DMA controller. So now let us take write an assembly language program to transfer 256 bytes from I/O to memory whose address is starting with 2050. So one memory address is 2050. So this is 8085, but we will add up 0 to 50 address. So command register is 88, mode register is 8B, current word count for channel is 80, and current address for channel is 82. This channel you have to use. So now the program is what? Write an ALB to transfer 256 bytes from I/O to memory. Okay. So now let us try to take the program. So now you have the command register, now you have the mode set register. So command register already we have seen. Now here command register contents. Okay. Now which channel now need to be used and all you can verify. So then 50 is the code need to be written, command word. Mode register. In mode register, here, it is B5. So the number of bytes needs to be transferred is 255. 255 equivalent is in hexadecimal is FF. So the count need to be loaded is 00FF. And the starting address of the memory is 2050. So this has to be loaded. And data is to be transferred from peripheral to memory. So then the DMA write operation. This is in DMA write operation. So now this is the code. So move AL comma 50. This is the command word. This you write it in your command register. So command register address is 80. Then count you. So now you load the count 82. 82 is what your address of the channel. Okay. So here move AL50, then 82 is what you load. Right, so 50, this is not 50, 82, 88 and 8H. So then 50 and 5H. So this is move AL comma, this is move AL comma B5. So this is AL comma B5 and then this is 8BH, command word and all. So this you write in command register and mode register, mode set register addresses. Right, then count is 2050. Right, so then you load the count, 50 you load, then out, 20 you load and out at that particular channel. Okay, the starting address of the memory is 2050. So 50 you load and give the starting. So here if you try to see the current word of the current channel, right, so that you can give it here. Right, and then count is FF00, give it at 83. 83 is your current address of the channel, right? Okay, and then move AL comma 00 and load it, and move AL comma B5. Yeah, this is what the sequence. So now what you do is this one you write in command word. So then you just write the address of the memory from where you want to transfer data. So lower and higher, and then the channel which you are using, load with the count, and then move B5 AL and then out BH. So then the next sequence is this. So the set register, when you write this, it will transfer. So it is very clearly written. A simple code of a piece of code. What you can do is, see here, the first one is command word. The first one is the command word, and next one is the location of the memory from where you are transferring. Next one is the count, and next one is you are writing in your mode set register so that it will transfer the data. So this is simple program. You can write it in your 8257 to transfer the data from IO for this kind of program. Write an ALP to transfer 256 bytes from IO to memory, and this you can take it as homework. Write an initialization program to transfer data from peripheral to memory to the following specification. Bytes are 256, memory is this, channel used 1. Earlier I used this different. So priority rotating mode, extended write is disabled, PC stop is enabled, and now the address mode set register and then the address of the channels are 82, 80 terminal count register is 83, and then this one and this one. So now you can write program, right? You can write the codes, the things, and then you can write the programs in this. Similar, you have a number of examples, and 827 can